EX87. Let's talk about the classification theorem of Dieudonne-Manin, which provides us a more concrete way of looking at Newton numbers, but this connection with Newton numbers will not be apparent here, but later. So let me first recall some definition, and then we have a related exercise, kind of a example to compute. Definition: let small k be perfect, let's say, field of characteristic P, and let small sigma wk isomorphic to itself be the Frobenius map. More precisely, automorphism. So lifting the Frobenius over K, which is the 1 maps x to x to the power P. Then we call Dieudonne ring of small k is the associative ring defined as follows. Denoted by d small k, defined to be w of k, f we how to write these letters elegantly? Let me think. Subject to the conditions or to the relation, so they are not two variables without relation, so there is a relation between them with actually yes, so the relation is as follows: f v equals v, f equals p. This is very similar as Frobenius and Washable. F how did I wrote this? Yes, okay. F C doesn't commute with elements of wk, but sigma of c, and c v equals v sigma of c for c w of k. This is the definition of Dieudonne ring. In particular, so such ring could see this discussed in Demesur's book on p-divisible groups. There is a classification of Dieudonne modules which classifies p-divisible group over, I guess, perfect fields. Remark: this ring is a non-commutative ring. Except when k equals fp. In that case, the Frobenius X trivially on ZP. And this is isomorphic to just Z, P, X, Y quotient by X, Y minus P. Wait, no, of course not. This is just, wait. Yes. Like this, because it's commutative, sigma c equals c for c in ZP, and so the last two relations are trivial. The only relation is f equals v of f equals p. So xy equals p, and why we don't need to say xy equal to f x, so which this is just saying it's commutative. So question, when we write the polynomial ring, do we mean the commutative ring or just a formally defined ring? Interesting. So actually what we mean is this is a commutative ring when we write this, right? This is when k equals fp. Second remark, so this dk invert p has a much simpler structure than d of k, because if we let k0 to be as you wrote, then dk invert p if the twisted polynomial ring, polynomial ring K0f, because you invert p and so f become the inverse, so we become the inverse of f, right? Not necessarily the inverse of f, but xy equals a unit, so f and we both become units. Your variable f satisfying the commutative relation f of c equals sigma of c f for or C in K0. Let's think it for a while. Where is the V going? Because let's say if F equals P, then y over pf v equals 1, and then with just so v over p is just the inverse of f. Right. And then that's not the reason you can remove that variable, right? Let me think. So equals P. I mean, this is sometimes this is implying that I should think of this, right? So I put a question mark. Twisted polynomial ring. Question mark, and also exercise to think about it. When you invert P, how is the structure of this dk1 over B? Should be at least like this, f and f inverse, right? And third remark, moreover, on left, the K module is the same thing as a WK module. D equipped with a semilinear endomorphism f from D to D and a sigma inverse semilinear endomorphism V from D to D such that f v equals v of f equals multiplication by p over d. So p, this is Teshmeter lift. Tensor lift of P inside W of K. Wait. Or in other words, let me think. Or you could just think of it as just multiplication by P over WK, but it involves the addition structure of the weight ring. Take element here. So P times this element means you do addition using the formal group law, P times. All right. The F Frobenius Verschiebung equal Verschiebung compute Frobenius. It's the same as multiplication by P, which means addition with itself, P times. Tensor map is multiplicative, so we could just have this condition in small k and then have similar condition, just apply the tensor lift in W of K. Okay, the second definition. An isocrystal over K0 is a finite dimensional K0 vector space D equipped with a bijective Frobenius semilinear endomorphism. Phi of D. So you see isocrystal here is not too far from just the phi module. Here is a condition which will only require this Frobenius to be bijective. Semilinear means over the coefficient K0 is the absolute Frobenius. So this is isocrystal, and this comes out to be a very important concept, and you could imagine how to classify it would be a very important thing. More things should be said why this is important. This will be more and more clear later. Remarked, this is abelian category. And we denote this abelian category abelian category of isocrystals over K0. It's denoted there is notion of tensor product in this category and due. I think seeing things like this is related with Tanaka category, but we'll not discuss it here. Now, very important example of isocrystal. This isocrystal will be seen as a building block later. Let K0 phi be dk invert P with phi equals f mentioned above. Be the twisted polynomial ring. Let me put a small remark. The twisted polynomial ring is isomorphic to the ring of additive polynomial, but where the multiplication on the latter is given by composition rather than Euro multiplication. So it's the twisted polynomial ring satisfying phi of C, phi composed with C element of WK equals sigma of C and then phi for sigma in K0. A class of isocrystals over K0 is given by the quotients. As follows: D R gamma S defined to be K0 polynomial ring over with phi, quotient by the ideal generated by phi to the power R minus P to the power S. for any integers, positive r and integer s. So s could be possibly negative. The Frobenius structure on DRS is defined by left multiplication. By phi by a division algorithm argument. So this is again the remark. See remark 1, remark 2, remark 3 by division algorithm argument. We can see, or one can see, that DRS has finite dimension R over P0. This is really a good exercise. I hope we could do that someday, but not today. And it is an isocrystal for K0. One would imagine that as phi is not linear. It's only linear when k equals fp. There is no good notion of eigenvalues. It's not linear transformation, so you cannot talk about eigenvalues. But there are something that will be very similar as eigenvalues. So I'm saying something without proof. We'll see this hopefully later. Eigenvalues on DRS that are so constant c, or let's say some integer n times p to the power rs over r. At this moment, this is not at all clear. Remark 5. Let small k bar be algebraic closure of k for any isocrystal D over K0, we get isocrystal over K0 on ramified completion equals WK bar invert P by scalar extension from K0 to this K0 on ramified hat, so we denote this by D hat. So endowed with bijective semi-linear tensor product. Tensor product for Venice. It's denoted by phi d hat, acts on elementary tensor. It's by our construction or our definition to be sigma c tensor with phi d. So this is consistent with our Frobenius structure over the tensor product. And there is a so-called Dieudonne-Manin classification. So one could find information about this on paper of Manin. Let me just quickly mention this. This is paper of Manin, 1963. Theory of commutative formal groups over fields of finite characteristic. Theory of commutative formal groups or fields of finite characteristic. That describes the possibilities or classifies the D hat. So let's mention there is a theorem for an algebraically closed field positive characteristic. The category of isocrystals over K0 isocrystals over K0 is semi-simple. Which means all objects are finite direct sum of simple objects and all short exact sequence splits. Moreover, the simple objects given up to isomorphism by the isocrystals we just described in the examples above, d r comma s, with greatest common divisor of r and s equals 1. So it's rational number. Remark. Firstly, the theorem tells that if K is algebraically closed, positive characteristic positive, then the isomorphism classes of simple isocrystals over K0 in natural bijection. With Q. Where a rational number expressed related with that DRS in the form S over R are positive, and then corresponds to DRS. Second remark, we will use triangle alpha to denote DRS. This is called a simple object with pure slope alpha. In this category, of isocrystals over K0 is still under the assumption K equals K bar. Thirdly, for any perfect field, small k with characteristic P positive, and any isocrystal D over K0, then let's re-summarize. Then the Dieudonne-Manin classification provides a unique decomposition since any element could be written as a finite sum, and here it says a unique decomposition of not isocrystal D, but it's a scalar extension to K0 ramified hat. In the following form. So D hat equals direct sum for alpha in Q, D hat of alpha for subobjects, D hat of alpha isomorphic to the triangle alpha we just described with some positive integer power, or with some integer power. And we see they having pure slope alpha. Pure slope alpha. And this is direct sum, so this d hat alpha equals 0 for all but finitely many alpha. For each alpha equals S over R and Q in reduced form with R positive, the integer dimension of this simple object up to raising some power. Over this K0 unramified completion is called the multiplicity. Multiplicity of this slope. So you have a slope. So you start with isocrystal. You have its d hat, and with this d hat, you have d hat alpha. This d hat alpha have a slope alpha, and also have multiplicity, right? This is the picture. So let me re-put this more precisely before give you the definition. So let me put this into a definition to make this more tidy. Let's first mention that the integer dimension of d hat alpha equals R times E alpha. This is because in previous we have mentioned that the dimension for ERS is finite dimension R, and here is raised to the power E alpha, so this is dimension R times E alpha is the number with multiplicity of eigenvalues. Of phi d with slope alpha. Definition. The rational number alpha for which in the decomposition, the alpha hat is not 0. So they are finitely many. They are called the slopes of D. And that dimension we have just mentioned is called the multiplicity of this slope. So the same number, give it two names. The first we call it the number of eigenvalues. And second we call it multiplicity of the slope. Okay. And we see that this isocrystal D is isoclinic with slope alpha 0 if this is not a 0 module, and is the hat is the same as just one component, one simple object, the hat alpha 0 for some alpha 0 rational number. In other words, it's called isoclinic if it's very simple, in the sense that this change is isomorphic to just this delta alpha 0 raised to the power e for some e. Now, finally comes our example or exercise for today. We want to look at a precise isocrystal and see how is the decomposition. Not give a general way, as you can imagine that could be very complicated, but let's look at very nice choosing example. So let K0 be fp squared 1 over p with p congruent to 3 mod 4. And remark, in this case you could see that the square root of -1 is contained in K0. In other words, I'm saying that x squared equals -1 have roots in K0 as solutions on K0. While in fp squared this is obvious. I think just take a tension lift. And now we consider the following isocrystal. the isocrystal, key 0 the base field, and we fix the bases E1, E2. So this is just telling you the structure as K0 module, nothing more. This is 2 dimension, but we have to describe what is this Frobenius. That's the K structure here on isocrystal. With Frobenius as follows over the spaces. So it could be described by, it's not linear, but I just use a matrix to tell you how to map the basis, and then you extend semi-linearly. We tell you it's given by the matrix as follows. In other words, phi d of E1 equal p minus 1 E1 plus p plus 1I E2. Phi d of E2 equals p plus 1I E1 plus minus p minus 1 E2. And then you extend uniquely by semi-linearity. So the characteristic polynomial, let me call this A. The characteristic polynomial for A, it's just the determinant of A minus lambda I. And that would be, if you compute, lambda square minus 4p. You just compute it. And so this implies that as roots lambda equals plus minus 2 square root of p. And so let's say lambda 1 equals lambda 2 equals, and so it's p-adic evaluation these two elements. This is 1/2 and 1/2. If we make this change, let's say E1 prime, we let it to be E1 plus I2. D2 prime, let it to be I1 plus E2. Remark that the Frobenius over K0 will map this I to minus I for the reason of P is congruent to 3-mode form. And we compute in the new basis. We have E1 prime and E2 prime. E1 prime is fixed, it has eigenvalue 2p. E2 prime has eigenvalue 2. And so the new matrix would have eigenvalues 2 and 2p with p-adic evaluations 0 and 1. Here is another remark. The map from WFP bar multiplicative group to itself map an element to Frobenius quotient by itself is surjective. Actually, this is a general fact. We would prove this maybe, but it's actually a lemma. Let me mention this. Let K be algebraically closed field, characteristic positive, then the map WK star, maybe omega to sigma omega over omega. It's surjective. This is the most general statement. We only take in particular example, take K to be FP bar. With this remark, let's continue back here. And we know that there exists some element in WFP bar such that sigma of C over C equals 1 over 2, right? And then let's further modify our basis to CE1 prime and CE2 prime. Then you say this phi D CE1 prime equals, this is semi-linear phi of C phi D1 prime sigma of C 2p E1 prime, and so this is sigma C over C 2p C times E1 prime, but then this is 1 over 2, this is p times C E1 prime. So if we change it to C E1 prime, then the eigenvalue become p, and CE2 prime, this become similarly before it was 2 times E2, now it's just C times E2 prime. It's stable. Just by this we could conclude actually that our D hat so working with small g equals fp, working with k0 wfp squared invert p, and so we take unramified completion. This is qp unramified completion. So let me put a remark. Actually, WFP R over P, so this is QP ramified completion. As you could imagine, this is also the same as the WFP square or ramified completion. And so this is now our QP, this is our K0. The conclusion is this is isomorphic to delta 1 direct sum with triangle 0. What is triangle 1? Triangle 1 is, recall, this is DRS with S over R equals 1. And SR coprime. So this is basically D11, which is K0 Frobenius quotient by phi minus P. And so Frobenius acting on it is the same as multiplication by P. Right, so this part is really isomorphic to C1 prime K0. So this has a Frobenius here, which is just multiplication by P. While delta 0 is just dr s with s over r equals 0, and so s equals 0. This is d0, whatever r, s equals 0, and so this is, let's say, d10. This is k0 phi quotient by phi. It's isomorphic to k0, which means the Frobenius here is trivial. And this is exactly the case with CE2 prime k0. Frobenius over the base is stable, is trivial, but only semi-linear over the coefficients. And so we got this description. So this computation here is not at all not systematic. This is just a very particular example, but it helps us to notice what are the important things when we classify those things. It's the Frobenius structure, right?